Alright, Assalamualaikum and good day. So next would be the second last learning unit, which is acid-base titration. So this is a continuation of LU4. Okay, but in this learning unit, we will focus more on the titration curve between acid and base. So this will be your learning objectives. So by the end of this learning unit, you should be able to illustrate titration of strong acid with strong base. Okay, and then describing the difference between endpoint and equivalence point. What does this two mean? Okay. Next is identifying the equivalence point in any acid-base titration based on the titration curve. Next is illustration of titration curve of a weak acid with a strong base. Okay, the next learning objective is distinguishing titration curve of polyprotic acid with a strong base as well as polybasic base with a strong acid. Next one is identifying suitable indicator for any acid-base titration. Okay, so this one you have done, okay, by using phenolphthalein in practical session. Next one is the application part of acid-base, which is Jadal analysis. And the final learning objective would be evaluation of acid-base titrimetry. So first of all, let us look at several terms in this that you will see frequently in this learning unit. The first one would be standard solution. So what does it mean by standard solution? Standard solution means a reagent that is used, okay, known concentration means you know its concentration, and the one that you will use in titrimetric analysis. Okay, so when you do titration, like the first experiment that you have done, you prepared standard solution of sodium hydroxide, okay, which will be used in the titrimetric analysis. Okay, so you know the concentration of the sodium hydroxide. So next term would be titration. So titration is performed by adding the standard solution that you have prepared, okay, from a burette, okay, or other liquid dispensing device, but normally we use burette for simple acid-base titration, to a solution of the analyte. Okay, so your analyte will be placed inside LMAF flask, and then you add in indicator to your analyte so that you will be able to detect the endpoint of the titration. Okay, the next point would be equivalence point. So what does equivalence point mean? Okay, it occurs in the titration at the point in which the amount of added titrant is chemically equivalent to the amount of analyte in the sample. So what does this mean? It's actually M1V1, M2V2 formula. Okay, so the amount of added titrant chemically equivalent. So M1V1 is equivalent to number of mole. Okay, so number of mole of the titrant chemically equivalent to number of mole of the analyte. So that's what it means actually. M1V1, M2V2. So let's say you start with 0.1 molar of 100 ml of analyte. Okay, and your titrant is 0.1 molar also. So you would expect the equivalence point occurring at 100 ml of the titrant used. Okay, so that is equivalent point. The next term is back titration. So what does it mean by back titration? So this is a process where you use excess of standard titrant. Okay, and that amount of excess use is determined back by back titration using a second standard titrant. Okay, in this back titration process, the equivalent point would be equals with the amount of initial titrant used. Okay, simply said, you don't know how much uh, analyte will react with the titration, but you know the concentration of the titration, so you use the concentration of titration in excess. Okay, and what is remain behind after the excess have with the analyte? Okay, you have find out the original amount of the sample. Okay, simple analogy. um, you want to buy biscuit at the supermarket, okay, but you don't know the exact cost of the biscuit, so you bring excess money. Let's say you bring 10 ringgit. Okay, once you purchase the biscuit, you get the balance. Okay, the balance of your money, which is 7 ringgit 50 cent. So from the initial amount that you use and the remaining that you get, you can actually um, identify the amount, the value of the biscuit, which is 2 ringgit 50 cents. So that's what back titration means. Okay, normally we use back titration in 3 different conditions. For example, the reactant is insoluble. Okay, insoluble, so we have to use back titration. Another condition is if the reactant or the analyte is volatile. Okay, so easily volatile, easily disappear into thin air, so you cannot use normal acid base titration, so you have to use back titration. Another condition is the reaction between the titrant and also the sample is too slow. So if too slow, then we have to use back titration. So you can watch this YouTube video where it gives you the detail of back titration. Okay, so the next term would be endpoint. So what is endpoint? Endpoint is when you do the titration physically, okay, experimentally. Okay, from there you get the endpoint based on the indicator used. So indicator will change color when you reach the endpoint. For example, you have done the experiment in the lab. Okay, first experiment. So you use phenolphthalein as your indicator. So initially, the color of the phenolphthalein is colorless, and when you reach the endpoint, it becomes pinkish color. So that is endpoint. Okay, the difference between endpoint and equivalence point. Equivalence is theory, M1v1, M2v2. Endpoint is when you do experimentally. Okay, like the example that I have given just now. So you start off with 0.1 molar of 100 ml analyte, and you titrate with using 0.1 molar of titrant, and you would expect you would need 100 ml based on M1v1 M2v2 formula. Okay, so that is equivalence point. But then when you do the experiment, you will tend to use more than 100 ml, let's say 100.2 ml. So that will that is endpoint. Okay, the difference between endpoint and equivalence. Okay, endpoint you do experimentally, equivalence is theoretically. Okay, so indicator is the one that you use to observe the endpoint. Okay, so the difference between the endpoint and the equivalence point, we call them titration error. So this is the formula relating to calculate titration error. The volume of the one that we use to do the experiment. Okay, this one is the volume that we calculate theoretically. Okay, the actual volume we use during experiment minus the volume that we expect to use theoretically. So that would be the titration error. So acid-base titration is actually a quick and accurate method for determining acid or basic substance in many samples. Okay, so very quick experiment because you only do titration, and it's rather accurate. Okay, if you prepare the solution carefully, you do the titration carefully. Okay, and the titrant typically used is a type of strong acid or strong base. Okay, the sample can be strong or weak, but we cannot use weak titrant. Okay, you can use weak titrant if your sample is also weak, but it's not recommended. Okay, So these are the 5 types of acid-base titration. Okay, the first one is titration between the strong acid and strong base. So the sample can be acid or even base. Okay. So if the sample is strong base, then the titration will be strong acid. If your sample is strong acid, then the titration will be strong base. The second type of acid-base titration would be between weak acid, strong base titration. So in this case, of course, the sample will be weak acid. Okay, the titration would be strong base. The third type of acid-base titration is strong acid, weak base titration. Means the sample is, or the analyte will be the weak base, while the titrant is the strong acid. The fourth titration curve is polyprotic acid with strong base. Okay, sample is polyprotic acid, titrant is strong base. The fifth one is polybasic base with strong acid as the titrant. Now first let us look at strong acid, strong base titration, the first one. Okay, so in strong acid, strong base titration, there are 3 important calculation involved. The first one would be the pH, okay, of the sample, okay, before equivalence point, the pH of the sample at equivalence point, and the pH of the sample after equivalence point. Okay. So let's see here. A strong acid titrated with a strong base. So means sample is strong acid, titrant is a strong base. So this is the reaction that we expect occurring. Okay, acid H3O plus with base OH minus. So this OH can be any type of strong base, KOH, NaOH. Okay. This one strong acid can be any strong acid, nitric acid, it can be hydrochloric acid. Okay, so the product, of course, neutralization with formation of water. Now before equivalence point, okay, sample which is acid, strong acid, is in excess. Okay, and how to determine the pH of this sample? We use this formula here. Okay, remember to find pH, you negative log H plus. So you negative log H plus to find pH. Okay, so the number of mole of acid will be in excess. So this one minus the added titrant, okay, which is number of mole of base. Okay, divide with total volume. Okay, total volume means the total volume after the addition of the titrant. Okay, the next part is equivalence point. What happened at equivalence point when you do acid-base titration? Okay, the number of mole of acid and number of mole of base will be equal. M1V1, M2V2 equal. Okay, but you don't calculate using the previous formula that I have shown, because if you calculate, you end up getting concentration of H3O plus as 0. Okay, so the pH you won't get 7. Okay, so this one you just write in terms of statement like this. Okay, equivalence point for strong acid titrated with strong base, you will get pH 7. Neutralization will occur. Okay, if you use the previous formula, you get end up getting H3O plus as 0. When you negative log H3O plus 0, you get error. Okay. Next is over titration. Okay, so what happened when you over titrate? When you over titrate means your titrant now become excess. So when your titrant now become excess, this is the formula you use. Okay, now your titrant is base. Okay, strong base. So this is the formula to calculate the concentration of base. Okay, now because it's over titrate. So OH is the millimole of titrate in excess over the total volume, and then you get negative log of this OH to get POH, minus from 14 to get the pH. Now to understand this better, okay, next we will look at example, okay, to understand the concept better. Okay, so this example is construct a titration curve for the titration of 100 ml 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. So this is a strong acid as the sample because you put 100 ml, okay, and you use titrant which is also the same strength, 0.1 molar sodium hydroxide, okay, strong base. Now remember the three points that I have discussed just now. The first is pH before equivalence point, secondly is pH at equivalence point, and thirdly is pH when you over titrate. Now first of all, the first step that you need to do is calculate the volume of the titrant needed to reach equivalence point, which is M1V1, M2V2. So when you use M1V1, M2V2, you know you would need 100 ml of the titrant also. Okay, same concentration. So this is 100 ml, so of course you would need 100 ml of titrant here. Now, the second step is calculating the pH before titration begin. So before titration begin, so in the Erlenmeyer flask would only be your sample present. Okay, the 100 ml of 0.1 molar hydrochloric acid. So how to find this pH of this solution here? Remember, you have covered this in the previous learning unit. Okay, you negative log concentration. Okay, so this negative log concentration will refer to H plus, which is the pH of acid. So if your sample here is sodium hydroxide instead, so you need to minus from 14 to get pH. So pH negative log 0.1, you get 1. So this is the pH before titration. Now next is when you start titrating. Okay, let's say we add in 10 ml of the titrant. Okay, 10 ml of sodium hydroxide. Okay, so of course the acid is still in excess. Okay, so when you calculate M1V1, M2V2, this one is still in excess. So the number of mole of acid minus number of mole of base, the one that counter. Okay, this one will counter the addition of the base. So 100 ml times 0.1, this one is number of mole minus number of mole of base over the new volume. Okay, initially 100 ml of the sample here, then you add in 10 ml, so it becomes 110. Okay, so from here it's already being calculated, 0.082 molar. So to find pH with negative log, because this is referring to H plus. So negative log this, you get pH 1.09. And we do it for the subsequent addition of titrant. Let's say 20 ml, 30 ml, 40 ml, 50 ml, 60 ml, 70 ml, 80 ml, 90 ml, and until equivalence point. And that has been calculated and plotted for you. Okay, from 0 to 90, and this is the pH change. Okay, so this is the plot. The plot will always be pH versus volume of titrant. Okay, so when you ask to do the plot, make sure you label it correctly. Okay, what happened at equivalence point? Remember I mentioned when the titration involves strong acid and strong base, the pH at equivalence point will always be pH 7. Okay. Notice the jump in the pH. 90 ml just before equivalence point. And equivalence, the pH becomes 7. Okay. So this is the plot. Okay, you see the pH gradually increase, and then suddenly at equivalence point it rises drastically. Okay. Okay, the next one will be over titration calculation. So when we over titrate, we add in the titrant in excess. Let's say we over titrate by 10 ml, means instead of 100 ml of the sodium hydroxide, we use 110. So 110 of the volume of the titrant times the concentration minus the number of mole of the sample inside. Okay, so this is referring to the original volume and concentration of the sample, the strong acid HCl. Now the total volume become 210. So the OH is 0.0048. You negative log this, you get POH. To find pH, minus from 14. So this would be the pH when you over titrate. Of course, you will expect it to be in the basic range. Okay, so you easily can detect you do mistakes here. When you forgot to minus from 14, you end up getting acidic pH, which is not logic. Okay, so we do it for the subsequent addition of titrant. Okay, let's say 20 ml, 30 ml, 40 ml until 200. And now let us see the plot. So this will be the typical plot for acid-base titration. Okay, so this is strong acid, strong base. Weak acid, strong base. Weak base, strong acid will also show you the same pattern. So this is a typical pattern for acid-base titration. The difference would only be probably start in the basic range and then finishes in the acid range. So this one is S, this one the inverted S shape. Okay, only that is the difference. Okay. Okay, let us see what happened during the acid-base titration. Okay, so initially here, okay, so this is your sample, HCl. Okay, so it's been ionized, okay, in solution. So you get H plus and Cl minus. Okay, this is before the equivalence point. Okay, notice that formation of Na plus from the titrant. So you have used, so the titration is between HCl plus NaOH. So you would get NaCl, this is the salt, and H2O. Okay, so that's why you see Na plus here. Okay, due to the formation of Na when the acid react with titrant, sodium hydroxide. So you see the formation of Na. So notice that H is decreases in number. Initially 2 present, now become 1. Okay, until at one point no longer H plus present, and this is where it reach neutralization. You only have the salt and H2O. Okay, H2O. Now when you over titrate, then OH now is present. Okay, OH is present from the titrant. Okay, so if we plot using POH rather than using pH, the result will still look identical. Okay, so typically we use pH. Okay, we use pH versus mil of the titrant added. Okay, so the curve of course will look inverted. Okay, so let's say if we start with acid sample like the previous example, we use HCl and we use strong titrant, which is sodium hydroxide, you will get this curve here. Okay, if we start off with basic sample, and your titration is a strong acid, you get this curve instead. Notice that the inversion point will be identical, except that the whether it start from acid or start from basic. Okay, still the same pattern. Okay, just that it inverted. Now let us look at factor of concentration. So concentration will affect the shape of the titration curve. Okay, so if you look here, this is what happened when we decrease the concentration of the sample, okay, of the acid. Okay, so this, let's say this is the original concentration, 0.1 molar acid with 0.1 molar strong base. So you get this pattern here. Let's say we dilute the sample, so it becomes 0.05 molar instead. So you start with at higher pH because it become less acidic. Okay, and if you dilute even further, or the concentration of the sample becomes more diluted, then the initial pH of course become more higher, so you get less distinct jump in the pH here. Okay, so that is the factor of concentration of the acid. Okay, salah. Okay, next we look at the concentration change of titrant. Okay, just now we have looked at the concentration of the sample. Okay, so you change, and there's the typing error, so concentration of a sample. Next we change the concentration of the titrant. So in this case, your sample is acidic, your titrant is strong base. Let's say we use this 0.1 molar sample, 0.1 molar titrant, so you get nice jump of the pH here. But then you reduce the concentration of the titrant, so the titrant now become 0.05 molar. Still a strong titrant, but you reduce the concentration, so you get less jump, okay, in pH. And if you reduce it even further, you get even less jump in the pH. So that is the effect of the concentration of titrant. Okay.